Have you ever wondered how you can get a perfectly exact answer in trig without even touching a calculator? Well, today we're going to unlock that secret. And it all starts with a quest to understand one of the most powerful, I'd even say magical shapes in all of math, the 45-45-90 triangle.
Okay, let's dive right in. Our journey here begins with a challenge, kind of like a mystery, and it's all centered on one of the most important angles you'll ever see, 45 degrees.
So here's the big question we're trying to answer. How do we find the exact value of sine of 45 degrees without a calculator? I'm not talking about an approximation, not that long string of decimals you get. When you punch sine of 45 into a calculator, it spits out something like 0.7071. But what number is that really? Where does it come from?
And that, right there, is the whole point of this quest. You see, in higher-level math or engineering or physics, those tiny little rounding errors, they can add up and cause big problems. We need pure, precise, exact values to build with. And that's where good old geometry comes to the rescue. So how are we going to solve our 45-degree problem? Well, we're going to call in the hero of our story today, the first of two magic triangles that just make trigonometry click. It's the isosceles right triangle. So, say hello to the 45-45-90 triangle. The name pretty much tells you everything you need to know, doesn't it? It's got angles of 45, 45, and 90 degrees. And because those two 45-degree angles are equal, the sides opposite them are also equal. It's just a perfect, symmetrical right triangle. You know, the best part is, we don't need some new complicated formula to figure this out. All we need is a tool you've probably known for years, the good old Pythagorean theorem. Let's use it to uncover this triangle secret. Okay, watch this, because it's so beautifully simple. To figure out the relationship between the sides, let's just say the two equal legs are each 1 unit long. Easy enough, right? Now we plug that into our theorem. 1 squared plus 1 squared equals c squared. That simplifies down to 2 equals c squared. You take the square root of both sides and boom, the hypotenuse is the square root of 2. And this is the triangle's secret power. It doesn't matter if the triangle is tiny or gigantic. If it's a 45-45-90, the ratio of its sides is always 1 to 1 to the square root of 2. That simple ratio, that's the key that's going to unlock everything for us.
Okay, so we've got our key. Now let's use it to crack the code of our main target, the unit circle.
But wait a second. We've got a problem. Our magic triangle has a hypotenuse of the square root of 2. But the unit circle, by its very definition, has a radius of exactly 1. And that radius is going to be our triangle's hypotenuse. So our triangle is too big to fit. What do? Simple. We just scale it down. I mean, think about it. To turn the hypotenuse from the square root of 2 into 1, all you have to do is divide it by itself, right? But to keep the triangle's proportions, to keep its magic ratio intact, we have to do the same thing to every single side. We divide them all by the square root of 2. So let's see exactly how this shakes out. Our original legs were both 1. We divide by root 2, so the new legs are now 1 over the square root of 2. The hypotenuse was root 2, we divide by root 2, and it becomes 1. Perfect! It fits the unit circle. Now just a quick side note. That fraction, 1 over root 2, is usually written a different way, as the square root of 2 over 2. They're the exact same number, but that second one is the standard form you're going to see everywhere. Okay, so this is the crucial part. When we lay this new, smaller triangle onto the unit circle, its legs literally give us the x and y coordinates. We did it! We found the exact point for 45 degrees on the unit circle. It's square root of 2 over 2, square root of 2 over 2. And from that single coordinate, we get all our answers. Remember, sine is the y value, so sine of 45 is root 2 over 2. Cosine is the x value, so that's also root 2 over 2. And tangent, that's just sine divided by cosine, which in this case is a number divided by itself, so it's just 1. No calculator, no messy decimals, just clean, exact answers. All right, so that's the theory, but let's see how this actually helps us solve the kind of problems you might get on a quiz or a test. Let's put this triangle into action. Okay, check out this example. What is the exact value of sine of 45 degrees plus cosine of 45 degrees? Now, without our new trick, you'd just be stuck with a bunch of messy decimals. But because we know the exact values, this is going to be surprisingly simple. So let's walk through it. We just substitute in the values we found. We know sine of 45 is root 2 over 2, and we know cosine of 45 is also root 2 over 2. When we add them together, we get 2 times the square root of 2 all over 2. And you can see right away the 2's just cancel each other out. And what are we left with? An incredibly clean, simple answer, the square root of 2. That is the power of using exact values.
All right, now before we wrap this up, let's go over a couple of super common mistakes that students make with this triangle. Seriously, knowing these can save you a ton of points on your next test.
Okay, here's a classic mix-up. People remember the numbers are 1 and the square root of 2, but they get them backwards. They put them in the wrong spots.
Wrong. Here's the easy way to remember. The hypotenuse is always the longest side of a right triangle. Always. The square root of 2 is about 1.41, which is obviously bigger than 1, so the square root of 2 has to be the hypotenuse.
And one more quick tip for you. While writing 1 over the square root of 2 is technically correct, in most math classes it's considered unsimplified because of that square root on the bottom. So we do something called rationalizing it to get the square root of 2 over 2. Just remember, they're the exact same number, but that second one is the standard form your teacher is going to be looking for.
So, there you have it. We did it. We took one simple magic triangle and used it to find the exact coordinates for 45 degrees. And by the way, that one triangle also unlocks 135, 225, and 315 degrees too. We've cracked a huge piece of the unit circle puzzle. But that just leaves one final big question. What other magic triangle is out there just waiting to help us unlock the rest of the circle?